so that we don't waste any time. So let's see the board now. Okay. All right. So if you can see the board, let me know. Okay, type it in charts if you can see this board. Can you see the board? Hello, Toby, can you hear me? If so, please type it, let me hear you. Type yes. All right, that's fine. Can you hear me? So I'm starting right away. So you tell me what I'm going to write on the board now. See, dealing with logic circuit minimization. That is combinational logic circuit minimization. Last time we discussed how to minimize logic circuit using Boolean algebra. We have used so many laws of Boolean algebra to minimize logic circuits, and we gave several examples. So today, we're going to continue from there. Logic circuit minimization. All right. Can you see me? So we can use several methods such as Boolean algebra. We can use Kanoff map. Kanoff. They call it K-map. K-map. Okay? And then we also logic. So those are various ways we can use. Today also we are going to talk about sum of products, and then the reverse of product of sum. Product of sum. All these, they are the various parts of logic expressions. When you have combinational circuits, you can have these two, convert one to the other using Boolean algebra or using the Morgan's theorem. The Morgan's theorem. Can you see the board now? Everybody, can you see the board, please? Confirm if it is clear now. Is it clear? Can you see the board? Okay, if it is not clear, let me see if I change the network, if it will be better. Another network right away. Is it clear? Somebody says it's still blurry. I want you to check now. Is it now clear? Can you read what I wrote on the board? Please check. So communicate with me through chat. Chat me up, please. So Michael still says no, it's blurry. We can't read it. Let me see. What can we do to that? Let me see if we can adjust that so that we can have a clear. Okay. Okay. What do you see now? Is it clear? If it is not clear, then we may not be able to hold this class. Please let me know if it is clear. If not, we will not be able to hold it. Is it clear now? Somebody says it's a bit clear. So let everybody check. Check what I wrote on the board. If it is clear, then I will be able to start. All right. Okay. Somebody says it's clear. So I want everybody to check if it's clear on your end so that I can start fully. I won't be able to continue if it is not clear. I want what is written on the board to be clear so that you can read it. If you can read it, then I will begin fully in this lecture. All right. Okay, it's fair now, all right? So we are going to continue. So last time, we talked about Boolean algebra, whereby we write expression for different combinational circuits like this. We have something like this: y equals a bar b plus a b bar plus a. This is a Boolean expression. It's not mathematics. It's not arithmetic. It's a Boolean expression that we can simplify to get the simplest form. Like I said, when you have a combinational circuit, you don't go ahead and implement like that. You need to minimize it. Minimize the output so that we can have the simplest circuit to implement that will save cost, save energy, save circuit space, save everything. So we need to simplify them. So today we are going to have several combinational circuits that we are going to simplify. We are going to use truth table to get the output of such circuits, and we are going to simplify them using a Kernoff map. Kernoff map. All right. So let's start. I'm going to use examples of combinational circuits to demonstrate that. So let's start from this combinational circuit that is given here. Then we are going to simplify it, drawing out the truth table for the circuit. I'm going to give out the intermediate outputs from gates and the final output from the gates. So let's see the board. This is what we are going to have. This is an AND gate. We have A and B inputs. Now it's a NAND gate. Actually, NAND gate goes out like that. Then we have another gate here. It is an XNOR gate. XNOR. So the output of this is C and the output of this is D. And then the input to this is C, A, and B. Take note, when it is connected, I'm putting a dot. When it is connected, when there's a terminal connected to tap a line, I'm putting a dot. When it crosses each other like this and there's no dots, it means they are not connected. All right. So these two outputs, we now move into XNOR. This one is XOR, and this other one is XNOR. XNOR, there's a bubble here, and the final output is Q. So we want to know what will be the outcome on the truth table for the output Q. So we're going to draw the truth table and see what will be the final output Q of this combinational circuit, combinational logic circuit. So let's check. We're going to draw the truth table like this. We have two inputs, A and B. Then we have intermediates, C and D. Then we have the final output, Q. Now this is what we have. When you have only two inputs, we're going to have four rows of inputs, which we know how to develop them as the first will be 0, 0, then 1, 1. And the next one will be 0, 1, 0, 1. How do we arrive at 4? When we have two inputs, it means 2 raised to power 2. We have two possible inputs, two possible values for each one of them, for the inputs. That is either 0 or a 1. Don't forget, we are dealing with digital electronics, and we usually talk about 0 and 1. So we have two possible outcomes for each of them, A and B. So that means we are going to have 2, 0 or 1, raised to power 2, and give us 4. So that's why we have 4 rows here, 2 raised to power 2. Now if it is A, B, C input, there is going to be 2 raised to power 3, 3 inputs, and possible value for each one is 0 or 1. So we're going to have 2 raised to power 3. That's the possible combination that we can have. So let's see what we are going to have at the output of C, A, B, into a NAND gate. If it's a NAND gate, what are we going to have? That is what we are going to put there here. For the NAND gate, 0, 0, it will be 1, 0, 1, it will be 1, 1, 0, 1, then 1, 1, it should be 0. Take note of that. All right? Then for this is XOR. XOR, you look at AB as input to the XOR and you write the output here. You not consider C. C is not part of the input to the gate here, to the second gate here. So what we do is look at each line, 0, 0, what is XOR? XOR will be 0, 0, 0, 0, 1, 1, 1, 0, 1, 1, 1, 0. So XOR does not allow each both inputs to be I in order to have a high. It allows only one of the inputs to be I for us to get an output, like we treated in a previous lecture. So either of the two will be I, then we're going to have the output. When both of them are I, there will be no output. And when both of them are low, there will be no output. So we have this. Now, the two outputs here, C and D, these are the intermediate outputs. That is, in between, they are not the final output. So they serve as the input to the final gate, which is actually X NOR. The final gate is X NOR. This is XOR, this is NAND gate. All right? So, what do? We use C and D as the input to the X NOR and write the final output as Q. Okay. So X NOR will be the reverse of what happens at XOR. So we are going to have here C and D will be the input. So you don't consider A and B any longer. You consider C and D as the input. We are through with A and B. So C and D, they are like the A and B here, serving as input to the final output gate. So what do? What we do is this. We look at 1 and 0 for an X NOR. 1 and 0 supposed to be 1 if it is X, XOR. For X NOR, then it will be 0. The 1 and 1, it will also be 0. Okay, 1 and 1 for X NOR supposed to be 0 for this. For here, it will be 1. 1 and 1 again, 1. 0 and 0, that means it's supposed to be for this case, 0 and 0 is supposed to be 0, but since it is X NOR, to be reverse of what happens here, then it will be 1. So the final output for this combination circuits is this Q, and we have 0, 1, 1, 1. Now, if you want to write it using Boolean algebra, what you write is a sum of products. Sum of products. Q. Now, the sum of product we are going to write, we are not going to write the expression for C and D, but for A and B. Now you look at 1 here, 1 here, 1 here. This is 0. This will not have an expression, the final output that we are going to write. What we have an expression is where we have an I that is 1. All these 3 positions where we have a high, then we write it. So we can have this. Q equals A bar B. A bar because A is 0 here. B, that is the combination here. Then here, plus A B bar. Then plus AB. 2 of them have a high. So this is the final output Q. That's the expression that we have here. That is the output of this combinational circuit. I hope that is clear. I hope everybody can see it. If you can see it, can you type it? Type it, and let me see. Type yes, that you can see the screen, you can see the board, and it's clear from your own end. All right? I hope you are jotting things down, because right now we are going to move on to the next example. The next example. Okay. So please confirm to me that you can see it before we go to the second example. I can see, okay, I can see people confirming that they can see. So right now I'm going to the next example, that is example 2. Example 2 also is a combinational circuit that's having only 2 inputs. So let's have that. Let's see example 2. Before I go ahead, before I rub this line, what I wrote down here is called sum of products. Sum of products. That is all of and gates. This is all. The addition here, the addition sign here, it means all gates. So right here we have AND gates here between A and B, between A and B, between A and B. A bar B, that's an AND gate. A B bar, that's another AND gate. A B, that's another AND gate. It's a product of these 2 inputs. So that is AND gate. And there is a sum between them, that is OR. So what we have here is called sum of products. We can actually convert it to product or sum, which we are going to see very soon. I'm going to see that very soon. So let's have the second example. We have an AND gate like this, going out to enter an OR gate to give us output Q. Alright, the input to this AND gate is, we have A at the start here, input A, then also we have input B with it, but input B is shared, input A also is shared between the 2 gates at the start. The second gate is a NOR gate, and the output of the NOR gate also goes out to the final OR gate. So we have input B here, input B, and then input B and A is shared. We have A entering here and B. Then from here also, we have B entering there. So we have AB into this, we have AB into the second one also. Those are the 2 inputs to this. Now let's develop the truth table for that. The inputs AB and then the outputs will be Q. But before Q, we have intermediates. The first intermediate that we have is here. The output of this AND gate will be A, B. And the output for this one, NOR gate, will be A plus B bar. The bar shows that there's a bubble here, which is actually a NOR gate. Then after that, we have the final output. We are going to get the final output Q. All right. So AB, we are going to have four rows: 0, 0, 1, 1, 0, 1, 0, 1. Then AB, from AB, that is a AND gate, 0, 0. For an AND gate, rather, we are going to have 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1. That is the behavior of our normal AND gates, the basic AND gates. Now for a NOR gate, let's see, you still consider A, B for it. 0, 0, since it's a NOR, 1. 0, 1, 0. 1, 0, 0, 1, 1, 0. That's what we're going to have for a NOR gate. Alright? Okay, now Q is an OR between these two inputs, between the intermediate inputs A, B, and A plus B bar. So we're going to consider these two now as input for the final OR gate. So what we have here will be 0, 1, 1, 0, 0, 0, 0, 0, 0, 1, 0, 1. And that's it. So the final output will be 1, 0, 0, 1. If you want to write this using Boolean algebra, we have Q equals, using A, B as the input for the entire system, we have Q equals A bar B bar plus A bar B plus, this is 0, this is 0, so only this we have an expression at the final output. This one is obtained from A bar and B bar as a product, and then the last one, A and B, A, B as a product. So that's the Boolean expression for the output Q. If you want to write it out as it is, that's the Boolean expression. If you want to write it out, and it's a sum of products. Okay, I think we get that. So we can move on to the next one now. Please like the live class. Can you give a like to the live class? Let's see your like before we move on to the next example, which is actually more combination, several gates connected together to form a combination circuit. Don't forget to give a like to this class, to this live class. I can see that we have 11 people connected here. Let everybody give a like. So yes, give a like to this class. Don't forget, if you're not subscribed to this channel, do so. We appreciate that. Subscribe to this channel. All right, give a like. I can see 2 likes here. Please let everybody give a like. We move on now to the third example. Give a like to the class. I hope you are jotting down. Now I can rub what we have on the screen now to write the third one. The third one. Okay, so let's move on. The third example is more complex than the previous two, and so we're going to have so many intermediate expressions before we get the final output. We have it this way: 3 inputs, logic combination circuits. We have AND gates starting with 3 inputs A, B, C. A, B, C. Then we have an OR gate somewhere not too far here for inputs B and C. So we are going to have a NOT gate for inputs B and C. Then input C. So what enters here now is not B and C, but B bar, C bar. The output of these gates is now entering another AND gate, which takes A as one of its input as well. A as one of its inputs. Remember, when the line crosses like this, it's not connected unless we give a dot like this. So the final output is an OR gate giving us output Q. Final output is an OR gate that gives us output Q. Okay? So we can show the final output after several intermediates on the truth table. So the output of this AND gate is an input to this. Likewise, the output of this AND gate is an input to this OR gate. So we want to develop the truth table for the final expression. We want to learn how truth table is developed very well. So what we do is to have a long table like this. Okay? The long table have several intermediates, and then the table has eight rows. Since we have three inputs, so we are going to have inputs A, B, C. So we can have 0, 0, 0, 0. You divide them into 2 first, then you write 0 first. Then you divide them into 2 again for the next one. 0, 0, 0, 0. 1, 1, 1, 1. Then the second one, divide 4 into 2. 0, 0, 1, 1. 0, 0, 1, 1. Then the last one, you have 0, 1, 0, 1, 0, 1, 0, 1. By now, you should know how to develop truth table for the inputs. The number of inputs that we have. If we have 4 inputs, then we're going to have 2 raised to the power 4 rows. That is 16 possible rows. And then if it's 16, we are going to have, first of all, 16 divided by 2. 0, 0, 0 in 8 places, 1, 1, 1 in 8 places. You go to the next one, 0, 0, 0, 4 places, 1, 1, 1, 4 places, and you fill it down. Then you proceed to the last 2 in this manner. Alright, the first intermediate we are going to have now is the output of this AND gate. So the output of this AND gate, we are going to have this as A, B, C. And the second one will be B bar and C bar. B bar, the third one will be C bar. These two, which will serve as input to this gate. B bar plus C bar. B bar plus C bar. That is what we are going to have at the output of these gates. Then this gate also, we are going to have this output and A. Then that one will give us A into B bar plus C bar. Then this last one and the first AND gate will now serve as input to the last one. Okay? So let's see. ABC for this first gate, ABC 0, 0, 0, 0, 0, 0, 0. AND gate will not have a high unless all the inputs to the AND gate is I. All the inputs are I. 1, 1, 1. That is when the output of the AND gate will be 1. When we have at least 1, 0, the output of the AND gate will be 0, unless all of them are 1, 1, 1. So here we are going to have, for the 7 rows, until we get to the last one, where you can obtain 1. Then B bar, look at B, and then you invert the sign here. B bar, 0 now will become 1, 0 again 1, 1 will become 0, 1 becomes 0, 0, 1, 0, 1, 1 becomes 0, 1 becomes 0. Okay? Okay? Now, C bar, we look at C, we have 1, 0, 1, 0, 1, 0, 1, 0. If you pay attention to the table now, you see that inversion of here is what we have here. Instead of 0, 1, 1, 0, 1, 1, 0, 1, 0, 1, we now have 1, 0, 1, 0, 1, 0, and so on. The same thing for B bar. 0, 0, then 1, 1, 0, 0, 1, 1, and so on. Then we want to do all between B bar and C bar. These two, we are going to do OR gate for them here. So we are going to have 1. If you can have at least one input is high, one input has 1, then we are going to have a 1. 1, 0, 1, 1, 1, 0. And that's what we have here for this output between B bar and C bar. Now, this final hand bit is having input from here and then input from A. So we're going to look at A and this column together to do a hand in this column. So this and this. Remember, for an AND gate to have an output as 1, the both input must be 1. If only one is 1, then the output is going to be 0. And if both of them are 0, the output is going to be 0. So let's look at it. A in this column. That's what we are going to use. 0 and 1, 0. 0 and 1, 0. 0 and 1, 0. Okay? All right. Okay. The fourth one, 0, 0 and 0, 0. Next one, 1 and 1, 1. 1 and 1, 1. 1 and 1, 1. 1 and 0, 0. So that is the output we are going to have. And that is the intermediate output at this point. Now, the final output Q is between these outputs, the outputs here, and the output of the first AND gate and here. So this ABC, we are going to do an OR sum between this ABC and A bracket B bar plus C bar. So look at this column and do an OR results to the final output Q. Okay, that is Q equals ABC plus A into B bar plus C bar. I don't know whether you can see this portion clearly, but don't worry, this is just Q. It's just Q. So let's look at it. This and this. Do an OR sum of the two. 0 and 0, 0. 0 and 0, 0 for an OR gate. 0 and 0 again, 0. 0 and 0, 0. 0 and 1, 1. 0 and 1, 1. 0 and 1, 1. 1 and 0, 1. And that's the final output, Q. So when you look at this final output critically, somebody will be able to clearly see that something is happening here. When you check it critically, that you see that that output looks like one of the primary inputs. Check it clearly. Look at this output and check these primary inputs, A, B, C. There is one that is exactly like this, and that is actually A. So what that is to say, the simplification of this entire combinational circuit is actually A. If you work it out by Boolean algebra to the simplest form, you're going to get the answer as A. And the truth table also has, clearly shown that. It verifies that the Q here equals to A. So if you go ahead and simplify this, the answer will be A. Because 0, 0, 0, 0, 1, 1, 1, 1, that's exactly the same what we have at the output. Isn't that very interesting? Very, very interesting. So I believe you can still see clearly the board. You can still see what we have on the board clearly. All right. Okay. Somebody is asking that about new equation. Well, this new equation, I didn't write it in full. Let me write it in full so that you can see it clearly. We have Q equals this plus this. That is what this Q is. Output of this with output of this, do an OR sum of them. So we have A, B, C plus A into B bar, that is this, plus C bar. That is the final expression for this Q. So by now you must understand what I wrote down on the board there. Is that clear? So if it is clear, you can see it, you can confirm to me on the chat. Please like this live lecture. Give it a like. I see only 2 likes. Let everybody give it a like. Like this lecture. And confirm to me that you can see what I wrote on the board clearly so that we can move to the next example. Next work. The next work is actually the Kernoff map. We want to learn about Kernoff map. We've learned how to use Boolean algebra to simplify logic gates. Today, we have seen how we can use truth table also to simplify and to develop truth table, very well. Right now, we want to go ahead to use Kernow map to simplify combinational logic circuits. Like I said from the start, I'm going to use Kernow map to simplify, like we've been using Boolean algebra. So, Kernow map is developed as another alternative to simplify combinational logic expression. Now, if you master Kernow map very well, you will eventually drop the use of uh, Boolean algebra. Because sometimes Boolean algebra fight to the last. We have the associative law, distributive law, commutative law, idempotent law, inversion law, and so on and so forth. Then the Morgan's theorem. We apply all of them in simplifying combinational logic circuit. Now we want to look at Kernow map. The man Kernow was a U.S. scientist that developed the Kernow mapping system. Now there are certain things you need to know about Kernow map to actually use it. One is that we develop maps or cells based on the number of inputs that we have. If you have two input logic circuits, you're going to use only 2 raised to power 2 kind of map. That is 4 cells. 4 cells. I'm going to have the cell that look like a box like this, whereby we have A on this side, B on this side. We're going to have A bar, B. And here we're going to have B bar, B. That's what we have. So this is for 2 input logic circuits, only 2 inputs. So we are now going to look at the expression from the truth table or from the Boolean equation and put the values of where we have 1 into the box, where we have 0 into the box. Now for a 3 input logic circuit, we're going to have 2 raised to 3 cells, that's 8 cells, and it's going to be like this. So we have 8 cells here, whereby we have A, B on this side, and C on this side. For the C, we're going to have 0 and 1, that is C bar, let's just put C bar and then C. That is what we mean by the 0 and 1. If C is 1, C bar will be 0. Alright. Now, for the AB, we're going to have A bar, B bar, A bar, B bar. Okay? We're going to have A bar, B, A bar, B, and we're going to have AB, and then we're going to have AB bar. That is the way the structure of a 2 raised to power 3, that is 3 input Kernow map. So you're now going to look at the truth table where you have 1, 1, 1, then you map the 1 into the cells. Each of these boxes stand as cells, and then we map only ones. We don't map 0. The ones that we map, they are actually as a result of the products of as a result of sum of products. Sum of products, like I showed you earlier, the equation that you wrote out for Boolean algebra, we have products, output of AND gates added together, that is sum of it, and or addition. So this is what we are going to do here. Wherever you have a 1 from your truth table, you place the 1 in the corresponding cell. We're going to see how we do that very soon. We're going to demonstrate it. If you have a 4 input logic, combinational logic circuit, we're going to have 16 cells. 16 cells. whereby we have AB on this side and CD on this side. So again, we're going to have A bar, B bar, A bar B, AB, AB bar. Then here we're going to have C bar, D bar, we're going to have C bar D, we're going to have CD, and we're going to have CD bar. So we're now going to map in the 1, 1, 1, 1 at the outputs of the truth table into the corresponding cells. You map them into the corresponding cells. All right. So after that, we are now going to go ahead and simplify what we have. So these are the basic knowledge you need to have regarding Karnaugh map. Let me also give you further rules for forming the Karnaugh map. When you have placed the cells, when you have placed, the 1, 1, 1 into the cells, then you need to do what we call mapping by drawing a circle around the 1, 1, 1s. And then you draw the circle in powers of 2. When they are close to one another, if 2 are together, you map them together, you circle them together. If 4 are together, you map them together. If 8 are together, you map them together. If 1, 1, 1 are together, you don't map 1, 1, 1 together. For instance, you can have 1 here, 1 here, and 1 here. You cannot map these 3 together. But rather, you can map these 2, and then you can map these 2. That means you are going to have 2 maps. But you cannot map the 3 of them. There's no way to simplify the 3 of them together like that. But for instance, if you have 1, 1, 1, 1, 1, 1, like this, we have 4, together. The 4 of them, 1, 2, 3, 4, they are like this. Then you can map them together like this. You have a map around the 4 because they can be captured together. If you have only one standing alone, for instance, you have 1 here, and there's no other one nearby, then you map that one alone. You must not allow it to go, it must be mapped before you do your simplification. You map it alone. Also, if you have 1, 1, 1 like this, you can map, since it's on the same row, you can have a map for the 3 of them like this, or if you do it 2, 2, you can map these 2 and map these 2, but the answer is going to give you the same results. Okay, but if this one is not here and it's here, you cannot map the 3 of them together. Alright? So we map in pairs of 2. 2, 4, and so on. 8 powers of 2. Now, every one that is present in the map, in any cell must be circled. But you must, by experience, you must know how to circle them. Sometimes one can be at the extreme here, another one at the extreme here, when there's no other thing in between. The 2 extremes can be mapped together. This is what I mean. Let us say there is nothing here. We have the map, the Karnaugh map like this. You have one at this extreme, another one at this extreme. You cannot map this one alone and map this one alone, but you map them together like this. The 2 of them are mapped together like that, because the Karnaugh map is understood to be, a kind of sheet that can be folded together and mixed. So if you fold this and fold this, they will meet somewhere. Then that means this and this will be together. So for that reason, we map this and this together as 2. Not one alone here, one alone here. Okay. So at the end of the day, after mapping everything, what next to do is to form an all sum of the products. Whatever you have here, you form an all sum of it. But before you form an all sum of it, you simplify what you have in each map. This will be simplified and write the answer down. This also, the same thing, this, and do an all sum for them, add them together. So how to simplify them is the most important part that we're going to learn now. But to actually do this, we are going to use an example to demonstrate what I've explained so far regarding Karnaugh map. Don't forget, we map Karnaugh map in powers of 2. That is 2 raised to power 1, 2 raised to power 2, 2 raised to power 3. 2 raised to power 3 is an octet. We call it octet. That is 8, cells together. 1, 1, 1, 1 in 8 places together. And that is what we do. So let's use an example to demonstrate. I believe you can see what's on the board clearly. You are following. If you can see that, please type "I can see" into the chat. Let me see that. Let everybody like this video, please. Give us a like. Give us a like. It's going to be more interesting soon. We're going to demonstrate Kernoff mapping using examples. If you can see, please let me see it in charts. I'm checking the chart now. Okay, I can see. Somebody said I can see clearly, sir. That's fine. So let's go to the next. So we're going to demonstrate using an example how to use Kernoff map to simplify combinational logic circuits. All right. Okay. So we have a combinational logic output written as this: F equals ABC plus ABC bar plus A bar BC. All right, A bar. Let me use our own notation. Our notation. A bar BC plus A bar B C bar. Now, when I said our own notation, there are two ways, to identify the bar. In some other textbooks, you can see it this way: A bar B C. Instead of using a dash on top of the letter, they use a complement sign on top of the letter. And that's another way to write this. So instead of using the bar as a dash on top, we use it as a complement sign like this. So this one will be like this. So that's what I mean. So our own notation in this class is to use a dash on top of the letter that we want to express as an inversion. Okay, so this is the equation, the logic expression given, or that we have got from combination output somewhere. Now we want to do combinational circuits, A, B, and C. So we're going to have a four cells in 2 rows. 4 cells in 2 rows. That is 4 columns like this. And here is AB. Here is C. Here is C. For AB, we're going to have, as I explained, A bar, B bar, A bar, B bar, then A bar, B, A bar, B, then the next one will be AB, and the last one will be A, B bar. And here, for this side, we have C bar and then C. Now, we now see how we place the 1, 1, 1 now. 1, 2, 3, 4. Each of them is carrying a 1. That is the output from the truth table somewhere. The truth table was drawn somewhere, and then these are the ones that carried 1 for the output F. So we want to place 1, 1, 1 where we can, on this chart, on the Kernoff map. So ABC, look at how we can locate ABC. Here we have AB, and here we have C. So we trace A, B, and C together. Then where they meet, that is where ABC is going to be. And we drop 1, a high output, we drop it there. Then AB, C bar. Look at A, B, C bar. AB, then C bar. C bar is here. So we trace them and they meet here. We drop a 1 there. Next, A bar, B, C. Look at this place. A bar, B, then C. C is here. Then you drop a 1 here. The next one, A bar, B, C bar. A bar, B, then C bar. So you drop a 1 here. So you have actually placed the I output in their right positions on the Kernoff map. So the next thing is now to simplify and write out an expression for them. Now, before you simplify, the job is to map it out. Map out the You can see that I mapped the 4 of them together. I did not map 2, 2, whether on the rows or on the columns. I mapped the 4 of them together because that's the highest power of 2 I can get. So you look for highest power of 2 first. If you can't find that, you look at the next, higher value, the next higher value, like that, until you map all of them. If you can't get, then if there's only one standing alone, then you map it all alone by itself. So we want to write an expression for this output. F equals what we have here. Now, what do we have here? Simplifying by kind of map. You look at the rows and the columns, and then you check which input stays constant, that does not change. The input that stays constant, that does not change, then you write it down. Then look at the column. If there's another one that stays constant, that is not changing, you write it as a product of the first one. So this is what we do. Look at this column and this column. Now, these other cells that we did not put anything, it means they were zeros from the truth table. So that's why we don't bother with them. All right? So this column to this column, that's where we have a 1 and a 1. And also from this row to this row, from row C bar to row C, we have a 1 and a 1. Now, we now trace column to column. You see the input that stays constant, that does not invert in sign. That is, if it was A, it remains A in the next column. If it was B, it remains B. If it was A bar, it remains A bar in the next column. That is the one we are going to write out. Now check out this column to this column. A bar, move here and change to A. We cannot use that. Then B, move here and remains as B. So we will write that one down. Next, look at this row to this row. C bar, moving from here to here, has changed to C. C bar has changed to C, so we will not write it. So for instance, if you have another column here, like if you have 4 inputs, if you have C and D, then we are going to have 4 rows, 1, 2, 3, 4. Then we look at all of them, all the maps that we have, how they move from one row to row, column to column. Now for this particular Boolean expression, the final output is what we have on the board. F is equal to B, because it's only B that remains constant. From here to here, B remains B. From here to here, C bar changes to C. So we remove that. From here to here, A bar changes to A, we remove that. We retain only B. So the final expression for this combinational logic output is B. And that is the simplification. Now, at your own leisure, you can go ahead, write this expression and use Boolean algebra to simplify. If you do it carefully, applying all the laws, you are going to come out with the expression F equals B. But now, you can now see the advantage of using kind of map. It gives you less stress. Once you map it carefully, you just check the row to row, column to column, and then you write out the expression as an OR expression of AND products. That is it. Isn't that very interesting? So I want you people to check. Okay, can you see that answer? How interesting is that? All right. Now, if you want us to also do it as a Boolean algebra, we can actually do it and get the same answer on the board. Let me quickly do that. So let's see what we have here. Starting from here, we want to simplify it using Boolean algebra. From here, we have F equals ABC plus AB C bar plus A bar BC plus A bar B C bar A bar B C bar. Now we can do some what was it called now? Factorization, like in normal mathematical algebra. We can factorize AB out from this first one, AB into C plus C bar. C plus C bar will now be 1. Then from here also, we can factorize A bar B plus A bar B into C plus C bar. Again, we have C plus C bar here. C plus C bar will be 1. That is 1 or 0. 0 or 1. 0 or 1 we always give 1 since it is an OR gate. So here, we now have AB plus AB bar. AB plus A bar B, rather. A bar B. Now, from here also, we can see that B is common. We can factorize B. B into A plus A bar. A plus A bar will also become 1. So the answer is B dot 1, which is actually B. So we can see that here, the Boolean algebra is applied and it gave us the same answer. But you can look at it that it took us some laws. We have applied some laws. For instance, here is distributive law. And the second row is C plus C bar. That is associative law, kind of, I think. And the last one is also distributive law. We did a distributive law again before we arrive at the final answer. So like I said, if you can apply your logic, Boolean algebra carefully, you will arrive at the same answer as Kernoff map. But Kernoff map will give you your final expression, more quickly than using Boolean algebra. Let's look at another example to actually demonstrate Kernoff mapping. I hope we are together. Can you see what we have on the board clearly? Are you following? Okay. All right. So let me move on now and go to the next example. The next example, we are going to have a truth table of output of a combinational logic circuit. So let me draw the truth table of 4x4, truth table of a 4x4 combinational logic circuit. So it's going to be very long, and we are going to see how we can use a Kernoff map to simplify that very easily. So let's see the table. Truth table is given. The truth table of 4x4 combinational circuits. We have A, B, C, D. And the output is given as output G. They gave us G as the output. Now, when we have a 4x4 like this, we are going to have 16 rows. That is 2 raised to the power 4. 16 rows. That's the possible combinations. Possible combination that we are going to have is 16. So we can write it this way: 0, 0, 0, 0, 0, 0, 0, 0. Okay. 1, 1, 1, 1. 1, 1, 1, 1. 16. The second one will be, that is first column will be 8 zeros, 8 ones. Alright? The next one will now be 4 zeros, 4 ones. 1, 2, 3, 4. 1, 2, 3, 4. 0, 0, 0, 0. 1, 1, 1, 1. The third one will be 2, 2. 0, 0, 1, 1. 0, 0, 1, 1. 0, 0, 1, 1. 0, 0, 1, 1. The last one will now be 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. All right. So these are the 16 possible inputs to the combinational logic circuit. Then they gave us the output of the truth table as this. We have 1, 0, 0, 0, 0, 0, 0. Then 1, 1, 1, 1, 0, 1, 1, 1. Very interesting. Very interesting truth table. So from the combinational logic circuit, this is the truth table that was generated, and we're going to simplify that using Kernoff map. So our Kernoff map is going to be 4 rows, 4 columns, 4 by 4. 4 by 4. Okay. Four by 4. Here will be A, B, and here will be C, D. So A, B, we are going to have A bar, B bar. Okay. We're going to have A bar, B bar. Next one, we're going to have A bar, B. We're going to have A, B, then A, B bar. The next one will be for the rows. That's for the column. Now for the rows, we're going to have C bar, D bar. We're going to have C bar, D. We're going to have C, D. And we're going to have C, D bar. Now, mark you, in some textbooks, you see, they will not use letters. They will use the digits, 0 and 1. So here, they will put 0, 0, 0, 1, you know, like that. Then 1, 1, 1, 0. Likewise here, 0, 0, 0, 1, 1, 1, 1, 0. What they mean is the real value on the table, 0 and 1s. Okay? So we want to map in the 1, 1, 1, 1 on this truth table into the Kernoff map. Our Kernoff map is standing there. So look at how we are going to map them in. Let's look at how we are going to map them in now. Okay. Anywhere we have a high at the output is where we are interested. All these 0, 0, 0, 0, we are not interested in them. So what we look at is wherever we have a 1 at the output. That one, we now look at the combination that gave that 1 at the input. The input combination that gave us the output of 1 is what we are going to map in here. Look at this one, for instance, starting from here. 0, 0, 0, 0, that means A bar, B bar, C bar, D bar. And that will be A bar, B bar, C bar, D bar. Here, you are going to have the 1. Isn't that interesting? Let's look at the next. This one, we have A bar, B bar, C bar, D. A bar, B bar, C bar, D. That is A. The next one, A bar, B bar, C, D. A bar, B bar, C, D is coming here. Then the next one, where we have a 1, is here. All this one, these containers, then you don't deal with those ones that are zeros. So here we have 1, 0, 1, 0. A, B bar, C, D bar. A, B bar, C, D bar. That is this position. We trace it from row to column and they meet together here. Okay. All right. A, B bar, C, D bar. Okay. That's all we have. The next one, A, B bar, C, D. A, B bar, C, D. This is C, D. We put 1 there. The next one. Okay, this is 0, this is 1. A, B, C bar, D. A, B, C bar, D. That is here, C bar, D. We place 1 here. Then the next one, A, B, C, D bar. A, B, C, D bar. Here. A, B, C, D bar. Then the last one, A, B, C, D. Very interesting. A, B, C, D. A, B, C, D. All the ones have been mapped into the Kernoff map. Okay? We've mapped all the bars into the Kernoff map. The next step is to now, map the 1, 1, 1, I, together. And map them carefully to ensure that none is left out. And then you mark them according to the rule. You mark them in form of octets, powers of 2. That is 8 cells together, 4 cells together, or 2 cells together. Or if there is anyone standing alone that cannot be mapped together with any other one, we map it alone. So let's look at this. How do we map this? Let me check what I have here. 1 1 1 1. Okay. Then 1 1 0 1 1 1. Okay. Let's check this carefully. Okay, we got this. There is another one here. A bar, B bar, C, D bar. 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 Okay. This particular one, I think the mapping of this one was not correct. A bar, B bar, C, D bar. A bar, B bar, C, D bar. We did not map it. We did not map it. We have 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. The main one. So I discovered that we left one out and it is here. A bar, B bar, C, D bar. That's this particular one is here. All right. I hope you are following. I can see somebody is asking a question. What if he forgets any law? We won't be able to get the same answer. Exactly. You must master your Boolean algebra. If you don't know your Boolean algebra very well, you may not be able to arrive at the final expression. It's simplified final expression. But one thing you must also notice that your Boolean algebra is similar to arithmetic algebra, whereby you can do factorization, collecting like terms, factorize, get a final expression. But when you are factorizing, you must be seeing what is happening and be remembering your Boolean algebra. For instance, the last one we had something like C plus C bar. A law in Boolean algebra tells us C plus C bar is equal to 1. So if you don't remember that, then you are hooked. You get stuck. You cannot progress. You cannot proceed. So you must be applying the laws as you are going. I think you get that. So that is it. So having this map, let's come back to the kind of map. Having this map, we can now simplify. After we have seen the 111s, we can now map them together and simplify. Let's see how to map them. We have 1 1 1 1. So powers of 2. We can map the 4 of them together like this. We have 1 1 1 1 here. We can map the 4 of them together, but we cannot map this one with them. This one cannot go with them. If it goes with them, then we're going to have 5. That is against our rule. We cannot map 5 together. Again, we can map these 2. Since this one is standing here and is close to this particular one, we map them together. Not minding the fact that we have mapped this one into this first map, to this map of 4 here. Not minding that we are still going to map these 2 together. That is how to do the Kernow mapping. So you can see that from here we have mapped all of them. There's no one left out. Somebody may ask, this one and this one, can we map them out like this together? Well, if you do that, it will be, excess. That's an excessive mapping. But of course, as with experience, you will know where to stop, where you should not map. Now let's write the final expression for this kind of map. G equals, what is the final expression for this map? The final expression for this one and the final expression for this. We're going to write them out as a sum. Now let's look at the expression for this. This column does not proceed to the next column. So we will not consider column in this case. But we see that this row is proceeding to here, and to here. So we check the rows and see the input term that remains constant. Look at this row. We have A bar, B bar here. We have CD, C bar, D bar, C D, C D bar. So as you are moving from here to here to here to here, we can see that we are moving from row to row, and some of the inputs are changing in sign. C bar, D bar, from here to here, we have C bar remaining C bar, but D bar has changed to D. So we cannot say C bar, D bar. We cannot write it out. The same thing goes for here. C bar has changed to C, even though D remains D. But C bar D does not retain its sign. Same way, CD does not remain as a CD. C remains as C, but D has changed to D bar. So we are not going to write that. So, in other words, the answer to this column will be A bar, B bar. It remains constant along the column. So the answer there is A bar, B bar, plus this 4. We're going to look at the 4 from column to column and row to row, since it's moving from row to row and column to column. From this column to this column, A remains A, but B has changed to B bar. So A is constant. Then from this row to this row, C remains C, but D has changed to D bar. For that reason, we're going to have A and C as a product. AC. A from, this column to this column, and C from this row to this row. This particular one. It's not changing from column to column, but it's changing from row to row. So C bar D, CD. From here to here, we can see that C bar has changed to C, but D has changed to D bar. Sorry, C bar has changed to C, but D remains as D. So from here to here, we have D. Is that not so? Then we also have AB constants along there. So we are going to write the 3 of them as a product. AB, then D as a product. AB, then D. And that's the simplified expression for this truth table. That's the final simplified expression. So if you look at the screen, you can see that it's very interesting using kind of map. Straightforward if you carefully map them out. Any question at this point? Do we have any question at this point? All right. If there is no question, we want to just focus on what we have there. Let's check another example, which will be the final example for today on that kind of map. The final example for today. All right. So I'm going to change the truth table now to another truth table. The input A, B, C, D will remain because we are going to have another 4x4 truth table and a 4x4 kind of map. So I will quickly change the truth table to another one by changing only the output of the truth table. So let me write with another, I want to write with another, column so that we can see that it's another example. Okay, so I want to put the output of the gates now. Output of the gates, that is the output of the combinational logic circuits. That is output G. We're still going to have output G. But here we have 0, 1. Next we have 0, 0. And then we have 1, 1. Next we have 0, 1. Another 0, 1, 1. 0, 1, 1. Okay, then 0, 1, 1 again. 0, 1, 1. And the last two will be 0, 0. The last two is 0, 0. Okay, so we are going to do the mapping for this and then write the final output for the combinational logic gates. Don't forget to subscribe to the channel, make your comments, like and share the video. I will personally respond to your comments at the comment section, so don't forget, make your comments, ask your question. I will attend to all the questions personally. So this is the kind of map, the 4x4 kind of map that gives us 16 possible cells for the output of the truth table. Now we're going to map them in. We're going to map them in now into the Kernoff map. Then we simplify accordingly. All right. So here we have a 1. A bar, B bar, C bar, D. A bar, B bar, C bar, D. This particular position. Here. Okay. The next one is here. A bar, B, C bar, D bar. A bar, B, C bar, D bar. That's a particular cell here. This particular cell. Okay? Alright? The next one is A bar B. A bar B. A bar B. Then C bar D. A bar B, C bar D. That's a particular cell here. Okay? A bar B, C bar D. And the next one, A bar B, C D. A bar B, C D, C D. This particular cell here. Okay? That is here. The next one here is A, B bar, C bar, D. A, B bar, C bar, D. This is C bar, D. This particular cell here. Okay? Alright? Okay. We have one here. One here. That is A, B bar, C bar, D. Alright? The next one is A, B bar, C, D bar. A, B bar, C, D bar. That is here. Place one there. Okay? A, B bar, C, D bar. Okay. Alright? Okay, the next one. A, B, C bar, D bar. A, B, C bar, D bar. A, B, C bar, D bar. That's here. Are we there? Then A, B, C bar, D. A, B, C bar, D. A, B, C bar, D. That's there. So let's check whether we have marked all of them. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Fine. So we have entered the ones into their respective position into the Kernoff map. The next thing is to circle them, mapping them according to the rules. Then we simplify it out. You circle them according to the rules. Then you simplify it out. So we have 1, 2, 3, 4. We can actually map those 4 together. And we have 1, 2, 3, 4. You can actually map the 4 of them together also. Then we have this particular one standing alone. There's no other one close to it. So we map it all alone. We map it all alone by itself. Okay. Then this one also, we have to map it together with the next one sitting close to it. So we have 4 maps. 4 maps. So we need to write out these 4 maps. What, they entail. So we can now say G equals this particular 4. We have A bar changing to A, B remains. Then C bar remains as C bar, D bar has changed to D. So we have B, C bar as a product. That's what you have here. That's what you have. B, C bar as a product. In this particular 4, we have, from here to here to here to here, they keep on changing. A bar, they keep on changing, but something remains constant. C bar D remains constant along the row. So you can write C bar. That is actually C bar D. That is C bar D. The next one, if you look at these 2, from here to here, C bar changes to C, D remains constant. A bar B, along the column remains constant. So we have A bar B, then multiplied by D as a product, because D retains its position, it does not change. The last one, that particular one, is going to be mapped out on its own and the answer written out for it alone. We have A, B bar remain constant, C, D bar remain constant. A, B bar, C, D bar. So that is what we have. That is the simplified expression from the Karnaugh map. That's what we have there. So if you pay attention, you now see that we have mapped them carefully and we have written out carefully all the expressions. Okay. So there's no one left out. And that's the final answer for the combinational logic gates that we have here. All right. So that's the last example we want to have. If you want to ask any question, please, you do well to ask in the comment section. Don't forget to like and share the video. And then in the next class, we're going to continue this lecture. Thank you for logging in today. So we see in the next lecture. Bye-bye.